Hello and welcome to another very entertaining video. For today's topic, I'd like to talk about the regulation of cardiac function. So, not necessarily what makes the heart beat, but what makes the heart beat faster, or slower, or more powerful. We can break this regulation down into two parts: extrinsic, those factors outside the heart that influence the heart, and then intrinsic, how the heart can regulate itself. And so for this first video, I'd like to just focus on extrinsic, and we'll follow up with a second video on the intrinsic regulation. Already illustrated is something that by now I hope you're very familiar with. This is the cardiac cycle. It's all about pressure. It's understanding how blood is moving from point A to point B within the heart. And then I just like to reinforce the idea that every time we see one of these lines cross a path, it's because we're flipping a pressure gradient, right? A pressure is going from low to high or from high to low, and we're flipping it. And whenever we flip pressure gradients, doors, valves, open or close. And we've got these labeled 1, 2, 3, and 4. We see at point 1, the mitral valve closes. Point 2, the semilunar valve opens. Point 3, the semilunar valve closes. Point 4, the mitral valve opens. And then we also recognize that whenever a door closes, that's something we can actually hear with auscultation. So at point 1, we have our first heart sound. Point 3, we have our second heart sound. Now what I'd like to do is overlay on top of this volume, specifically ventricular volume. And I always like starting where the volume isn't changing. And that's actually fairly easy to detect. For example, between point 1 and point 2 here, at the time when the mitral valve closes, but before the semilunar valve opens, both doors are closed. This is what's called isovolumic or isovolumetric, because the volume of blood can't change because both doors are closed. All the exits are blocked. Now at this point, we know that the volume inside the ventricle is at its max, and so we can label this as our end diastolic volume, or EDV. And between points 1 and point 2, it's going to be static. It's going to be a flat line. Of course, we can argue the same thing from points 3 to point 4, because this is after the semilunar valve closes, but before the mitral valve opens. Again, both doors are closed, so it's isovolumetric between 3 and 4. Now that we've ejected a lot of the blood, we see a similar thing. We see a flat line, static, no volume change. This is my ESV, or end systolic volume. And then, of course, if we're following the volume graph, when that semilunar valve opens, we eject blood fairly quickly. It starts to taper off. So we have a line that looks like that. Of course, at point 4, the mitral valve opens, and we have rapid inflow. This is a rapid 2/3 that quickly comes into the ventricle from the atrium. It's about 2/3, tapers off a little bit, and then we get that last 1/3 from atrial contraction as it forces its blood into the ventricle. And now we're back up to end diastolic volume. So just as a quick review, this 2/3 filling is passive, no contraction required. This last 1/3 is active, as it's associated with atrial contraction. Now, hopefully that was all review. Hopefully that was review. And what we want to do now is we want to jump in and start understanding how we might change some of these parameters to meet the needs of the individual. If I'm exercising versus sleeping, in a state of sympathetic fight or flight, whatever the scenario is, I need my heart to match my body's needs. And we want to show you how that's done. All right, to continue with this discussion, what we need to do is we need to define a couple of things. First of all is stroke volume. And I've added that there as defined as end diastolic volume minus end systolic volume. In other words, this is the amount of blood that's actually ejected following or during ventricular contraction. And we can actually see that on our graph as this amount right here, end diastolic volume minus end systolic volume. Now let's get some numbers to this. For an average individual, an end diastolic volume might be 120 milliliters. An end systolic volume, what's left over after ejection, might be about 50 milliliters. And so if we subtract 50 from the 120, what do we see? We see 70 milliliters as an average stroke volume. Now, cardiac output is going to build on that. Cardiac output says how much blood is being pushed by the heart over time, in this case, every minute. So we're just going to take that stroke volume, in this case 70 milliliters per beat, and we're going to multiply that by heart rate. An average heart rate might be about 70 beats per minute. And if we do that math, it's easy to see we come out with about 4,900 milliliters per minute. In other words, that's how much blood the heart is moving over any given minute. Now, I do want you to take a second to realize how much that is. I think Americans that don't understand the metric system very well don't recognize the sheer volume. We're looking at almost 5 liters per minute. So let's think about that in terms of something you're familiar with, cups, right? This is about 20 cups per minute. And now if you consider 60 minutes in an hour and 24 hours in a day, this comes out to be over 1,800 gallons of blood pumped by the heart every day. That's a tremendous amount of volume to think about. And the fact that the heart just does it day in and day out for year after year, it's pretty amazing. Now, there is one more calculation that I want to throw in here. And let's talk for just a second about ejection fraction. This is simply defined as the percent of the end diastolic volume that's actually ejected. Like we said, we recognize that not all of it is being ejected. There's going to be some left over. And this is actually a fairly easy calculation. This is simply going to be stroke volume divided by my end diastolic volume to give me a percentage. And so if we continue to use the numbers that we've been looking at, the stroke volume we had was 70 milliliters. The end diastolic volume we had was 120 milliliters. And to get a percent, we want to multiply that by 100. And in this case, that gives us 58%. And that's good because we're reminded that anything greater than 55% for males, it might be a little bit different for females. This is going to be what we would consider average. And so our numbers work. But now let's get back to a scenario where I want my heart rate to go up. I'm exercising, I'm running, I'm lifting weights, whatever it is. I want my heart rate to go up to meet the demands of both oxygen delivery to my tissues and carbon dioxide and waste removal from my tissues. This is all about what blood is doing. There are 2 systems that we want to look at as we think about extrinsic regulation. The first is simply autonomic control, and the second is the baroreceptor reflex. Let's go back and let's talk about autonomic control. We can, of course, break this down into sympathetic and parasympathetic. Sympathetic system will have 2 inputs. These are going to be sympathetic nerves, and these postganglionic neurons will deliver norepinephrine, or it could be a fight or flight response where we have epinephrine as an endocrine signal in the blood. But for our purposes, it's not going to matter. Whether it's epinephrine or norepinephrine, both of these neurotransmitters are binding to the same receptors. These are going to be beta-adrenergic receptors, specifically beta-1 and beta-2. In this case, both of them are going to be stimulatory. The difference is that we're going to find one type on one type of cell and another on another type of cell. And this is a little bit different than the parasympathetics. For sympathetics, we see a response for both autorhythmic and contractile cells. So let's look at each one of those individually. The beta-1 is on an autorhythmic cell. Remember, these are the pacemaker cells of the heart. Epinephrine or norepinephrine bind to the beta-1 receptor. This is classic G-protein coupled receptor signaling. This will lead to the generation of cyclic AMP. And if you recall, in these cells, the pacemaker potential is defined by the functionality of an HCN channel, which stands for hyperpolarized activated cyclic nucleotide gated. Well, there's our cyclic nucleotide right there, cyclic AMP. So when epinephrine or norepinephrine bind to these cells, it induces the production of cyclic AMP. Cyclic AMP binds directly to funny channels, my HCN channels, and it has the overall effect of increasing sodium permeability in these channels. So as cyclic AMP binds, these funny channels open wider for sodium, sodium rushes in faster, and this increases the slope of the pacemaker potential. And of course, if that slope is increased, what that means is that I hit threshold faster, the frequency of action potentials increases. In other words, I've just increased my heart rate. Now the beta-2 receptors work on a similar principle, but these are on the contractile cardiomyocytes. Same principle. It's a G-protein coupled receptor. We're going to activate the downstream effectors. And in this case, what we're going to do, just to keep it short, is we're going to increase calcium permeability. And this is through the L-type calcium channels, the voltage-gated channels, that are open during the plateau phase of the action potential of the cardiomyocyte. And the take-home message here is increased calcium coming into the cell equals stronger contraction. So to summarize, for the sympathetic system, working through both beta-1 receptors on the autorhythmic cells and beta 2 receptors on the cardiomyocytes, we get an increased heart rate by modification of the funny channel, and we get a stronger contraction as we modify the L-type voltage-gated calcium channel in the cardiomyocyte and increase calcium permeability. So let's go back and look at the parasympathetic system. This works primarily through the vagus nerve, cranial nerve 10. One key difference is that this is just autorhythmic cells. We only see muscarinics. This is going to be muscarinic M2, but it's only on autorhythmic cells. And you can appreciate it's just going to do the opposite. It's going to block what sympathetics do. And so this, while not affecting the strength of the contraction, will have the overall effect of slowing the heart rate down. In other words, it flattens the slope of the pacemaker potential. All right, let's look at the next one then, this baroreceptor reflex. The baroreceptor is part of a classic homeostatic reflex arc, and its job is to measure blood pressure. Two locations for baroreceptors: the aortic arch, the carotid artery at the bifurcation where the common carotid breaks off. And as a classic stretch receptor, if we were to, for example, just go in and take a cross-section of the aortic arch, we'll say this is normal stretch. And as such, because these are stretch receptors, there is going to be a frequency of action potentials going to the brain. So let's say the frequency is like this: 1, 2, 3. Not too fast, but not too slow. Well, what would happen if blood pressure was low? We see this, for example, you've been sitting in the hot tub for half an hour. You've vasodilated all of your blood vessels in your legs, and your blood's sitting out in your legs. And the minute you stand up, you leave all that blood in your legs, and it's not in your heart, and therefore not being pumped to your brain. And so what happens to the stretch receptor? It decreases in size, right? This is low blood pressure. The stretch is decreased, and therefore the frequency of action potentials goes down. Maybe it's like this: 1, 2, way over here. That decreased frequency of action potentials feeds back onto the control center, which is the medulla oblongata. That's going to send what response? Well, if my blood pressure is low, how do I increase it? I want to increase it through a sympathetic stimulation of the heart to increase blood pressure. And we talked about how sympathetics are working just previously. Well, what if my blood pressure was high? Well, in this scenario, stretch is going to be increased. And with increased stretch of my stretch receptors, I have an increased frequency of action potentials. Boom, 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 boom. The medulla oblongata registers that as a too high a blood pressure, and what's it going to do? We're going to stimulate cranial nerve 10, the vagus nerve. We're going to send the parasympathetic response to the effector, which is the heart, and we're going to slow the heart rate down. And that's the idea of the baroreceptor reflex. We're just measuring pressure by a measure of stretch. The more stretch there is, the higher the pressure. And then, as part of negative feedback, what do I want my response to be? If my stretch is high, I want my pressure to go down, so I want to decrease my heart rate. If my stretch is too low, I need to increase my heart rate, and I need to make my heart beat stronger to increase the blood pressure. So those are the two main types of extrinsic regulation, driving both the strength and the rate of the heart.